In this video, I'm going to describe how to use the future value function in Excel to calculate the future value of a lump sum, the future value of an annuity, and then we're going to work through a retirement problem, a fairly straightforward retirement problem, using the future value function and the present value function that was covered in a previous video. So in this first spreadsheet here, titled Simple FV, or Simple Future Value, we have this situation where we have $1,000 that was invested at the beginning of a year, and the rate of interest on this $1,000 deposit is 10%. So the interest earned during the first year, we are $100, which is 10% of the $1,000. So at the end of the year, we have $1,100. At the beginning of the next year, then, we have $1,100, and we're going to earn 10% on the $1,100 now. So at the end of the year, we have $1,210. And this is referred to as compound interest, or compounding, where we earn interest on the interest. At the end of the last year down here, after 10 years, we can see that we have a total amount in our account of $2,357.95 plus the interest we earn on that during the year, or $2,593.74. Now, there's no need to go through this type of a table to calculate the future value of a lump sum. Instead, we can just use the future value function in Excel. And for that, we're going to just put in equals FV, open parentheses. The first item we have is the rate, and our rate here is going to be 10%. Our number of periods here is 10, so we're finding out how much this $1,000 that's invested at the beginning of the first year, the first time period, is worth 10 years later. Our payment is equal to 0 because this is just a lump sum. Our present value is going to be that $1,000, and we want to make this a negative number so that we end up with a positive number. So we made a $1,000 cash outflow, so I'll put negative 1,000 for our initial cash outflow. And then the last item here is type. Well, in this case, type doesn't really matter because this is not an annuity, this is a lump sum, so we could put 0 or 1 here. Or you can just choose to leave that blank and just not include that in your calculation. So here's your answer, $2,593.74, which matches what we got in our table. Okay. So let's move on now to the annuity. And our annuity here says our annual deposits are $1,000, and it's made today and at the beginning of each of the next 9 years. And that's important because this is going to be an annuity due, because we're making our first payment today, and then we're going to make a payment at the beginning of each of the next 9 years. If this were a regular annuity, we wouldn't make our first payment until the beginning of, the end of year 1 instead of at the beginning of year 1 or today. So the account balance at the beginning of the year is 0, but we're going to make a deposit today of $1,000, and during the year we're going to earn $100 on that deposit. So at the end of the year we have $1,100. The beginning of year 2, we have $1,100 already in the bank. We're making an additional deposit of $1,000. So the total amount that we're going to have is $2,100, and we're going to earn 10% interest on that. So at the end of the year, we have $2,310. And we continue to do this for 10 years. And so at the end, we should have $17,531.17. Now again, the one reason why we use Excel is to make things simple. We don't want to have to create a table every time we want to calculate the future value of an annuity. So I'm going to go ahead and show you how to do that down here. We put in the function equals FV, open parentheses, our rate is our 10%. Our number of periods is 10. Our payment is equal to 1,000, and I'm going to make this a negative number because it's a cash outflow. We're investing out of our pocket $1,000 once per year. Our present value is 0. Even though it says we're making a payment today, the way we're going to set this up as an annuity due, Makes it so we don't need to put a value in for that present value. And this is important here. We want to put a 1 in because this is an annuity due of the type. It can be a 0 if the first payment's made at the end of the period, but that's not the case here. It's going to be made at the beginning of the period, so it's going to be a 1 here. And we get the same answer as we do in the table of $17,531.17. So the next one we're going to look at is kind of a simplified version of the classic retirement problem in finance. The retirement problem in finance is something we see a lot and we use a lot because it requires us to think about cash flows over time and cash inflows and cash outflows and calculating, making sure we have the right amount of cash for when we want to start paying out payments in the future. And so in our example here, our situation looks like this. We assume that we're going to be able to earn a 7% interest rate on our investments, and that's not, too outlandish. Things like bonds or fixed income investments generally earn about 4 or 5% over time, and stocks earn about 10 or 11%. So somewhere in the middle there is probably a good estimate on what we should be able to expect to get on our return on our investment. And we're saying that we expect to live for 8 years after retirement. Hopefully that's not the case, but we're going to make an assumption here that it's for 8 years. And for each of those 8 years, we want to be able to pull out $30,000. Okay, so we're going to start with a very simple assumption that we need $240,000 because that means every year we can pull out, for 8 years, we can pull out $30,000. So 8 times 30 is 240. Because we're going to make a deposit for 5 years at the beginning of each year for 5 years, we're going to divide that $240,000 by 5 to figure out what our kind of beginning payment should be. So that's what I'm going to put in here. I'm going to put in equals 240,000 divided by 5. So that gives me an investment of $48,000 at the beginning of each year. And if we do this, and again, this is not taking into account being able to earn interest on our money, we would end up with $178,140.29 at the end of our life, at the end of our retirement. And we don't want that. We want to invest the minimum amount to get to the value that we need for our retirement. So we're going to start off in this case using Solver to determine what that payment should be, what that annual deposit should be to get us to 0 in this value here. So I'm going to go to Data and Solver up here. Again, if you don't have Solver installed, what you'll want to do, and I'll close this out, you'll want to go to File and Options. And under Options, you'll go into Add-ins. And under Excel add-ins, you'll want to select Solver add-in here. And you want to use the solver that's under your data menu item. There is one that's out here. Sometimes it'll show up. This is not the solver that you want. You want the solver under data. Okay. So I'm going to select Solver here. And I want to set my value at the end of my retirement time period. So that's cell E19, and I'm just going to fill this in. Actually, I'm going to reset everything on here, just so we start from scratch. So I'm going to set my objective 178,140.29. That's the value in it right now. I want to set it to a value of 0 because I want to die broke. That's the goal. Just invest enough that you die broke. Okay, you don't want to have not enough money, but you don't want to have any money left over either. And now I'm going to say I want to do that by changing the cell in the annual deposit. How much do I need to invest? So Solver works its magic and comes up with a value for me here. I'm going to keep my solver solution. And it says at the end of my 13-year period, my 8 years of retirement, I will have negative 18 cents in the bank. And the bank can get mad at me for that. But that results in an annual deposit of $31,150.58. So now we're going to take a little bit of a look at this and see where we came up with that, and another way to get to that number without having to have a table here and without using solver. So I'm going to skip forward a little bit here to the spreadsheet that's called retirement picture. Okay, so the retirement picture kind of breaks up what we have. And the classic retirement problem is a two-part problem where we first have to determine how much money we need, and then we figure out how much we have to invest every year to get there. So my number is going to be off by just a few cents. As you can see here, my annual deposit says $31,150.60 instead of $31,150.58, which is what Solver gave us. So it's going to be off by a few cents. But let me show you where we get these numbers. So first of all, I want to withdraw $30,000 at the beginning of the year for 8 years. And so I'm going to start down here. And so this number represents the amount of money I need to have at the beginning of this 8-year period. So at the end of year 4, at the beginning of year 5, I need to have $191,678.68. And I'll just go through the explanation as I put the function in here. So to figure this out, we need to use a present value formula, or the present value function. So we're calculating the present value of an annuity. The rate of return on our invested funds is 7%. Again, I expect to live for 7 years. Oh, excuse me, not 7 years, 8 years after I retire. And I want to pull out $30,000 at the beginning of each year. So my number of periods is 8. My payment is $30,000, and I'm going to make that a negative number here. Okay, so negative $30,000. My future value at the end of this 8-year period is 0. I want nothing left in the bank. Kids aren't getting anything. It's all done at the end of my retirement. And my type, and this is key, is 1. Because I'm taking out the payments at the beginning of each year. So this is an annuity due. So that's what my function is going to look like here. And it gives me that value that we saw before, $191,678.68. So now I need to find the future value, or excuse me, the payment amount that gets me to that number. Okay? So the payment amount that gets me to that number, I'm going to delete this here. And I'm going to calculate the payment as equal payment. My rate is 7%. My number of periods is 5 periods. So this is a little, we have 1, 2, 3, 4, 5 periods we're going to put money in the bank for. Our present value is 0 because we're not starting with anything in the bank. Our future value, we want to have this $191,678.68. Okay. And then our type is going to be 1 because we're going to make each of these payments at the beginning of the period starting today. We're going to make a payment today, and then we're going to make 4 more payments into this account after today at the beginning of each year. So the payments are going to occur today at the beginning of time 1, the beginning of time 2, the beginning of time 3, beginning of time 4. And so those are going to be our payments. And then we're going to start withdrawing at the beginning of the next year. Now this is going to show up as a negative number because we put in a positive number for our future value there. Okay, but it's the same number as what was in there before, except for it's negative now. To make it a nice positive number, I can put a negative sign in front of that payment. So we need to make payments of $31,150.60. So now let's go to the next spreadsheet and kind of finalize everything here by putting in, again, those equations that I just described for you. The present value of the withdrawals. So we start with the present value function. Our rate is our 7%. Our number of periods that we're going to withdraw over 8 periods. We're going to withdraw $30,000, and I'm going to make this negative to get a positive number. And then the type is 1. Oh, excuse me, the future value is 0. And then the type is 1 because we're going to make these at the beginning of the period. And so again, in your mind, think about this is the amount of money I need to have when I retire to get the payments that I want out. The reason why this just isn't $240,000 is because we're earning interest on the money that remains in the account, the money we haven't pulled out yet. To get to that annual deposit over 5 periods, we're going to put in equals payment. Our rate is again that 7%. Our number of periods is 5 because we're going to make payments into the account for that many number of periods. Our present value is 0. Our future value, again, let's make this negative so that we get a positive number here. So we need to have $191,678.68 at the end of the 5-year period, or excuse me, at the end of the 4-year period, really, because we're making our first payment today. And then we're making our payments at the beginning of the period, so there's going to be a 1 there. And we come up with the same answer as as we got before, of $31,150.60. Please let me know if you have any questions about the calculations here and the idea of this retirement problem. It can be a kind of a complicated problem to think about, and hopefully this helps you out with that.